Our third type of category for ionic compounds is those where the metal contains a variable charge. With groups 1A, 2A, and the top of 3A, the charge of the metal depends on what group it's in, but most other metals have variable charges. These metals with variable charges are transition metals and post-transition metals. The post-transition metals are the metals under the stair-step of metalloids. There are a few transition and post-transition metals with only one known or common charge. Yttrium and scandium, which are always +3 as ions, and zinc and cadmium, which are always +2 as ions. You can think of them like bookends on the B section of the periodic table. As a bonus preparation for your exam, try to think about the electron configurations of those metals and the ions that they form, and make a guess about why they would have the particular charges that they do. When a metal has a variable charge, we're going to need to specify that charge as part of the name. If we do not specify it, there's not going to be any way for someone to go from the name to the formula. On the other hand, with the main group metal, we can go from the name to the formula because their charge is tied to the periodic table. Remember, we will need to know the charges before using the crisscross rule. The way we specify the charge is by putting it in Roman numerals in parentheses right after the name of the metal with no spaces. For example, in the name lead-2-sulfate, the 2 in the Roman numerals in parentheses is how we specify that the lead has a +2 charge. Notice that the metal is still taken directly from the periodic table, and in this case, sulfate is a polyatomic ion, so we use just the name of that polyatomic ion. We can write the lead sulfate part first and leave ourselves a blank in the parentheses to fill in for the charge. If we want to go from the formula to the name with these particular compounds, it's going to be a little bit trickier than what we've done before. We're going to have to figure out the charge of the metal so we can put it in the parentheses. The charge of the metal is going to be based on what that metal is bonding to and how many of that ion the metal is bonding to. Also, something to keep in mind is that if we have more than one of a particular metal ion within the compound, that is, if the subscript is greater than 1, then that Roman numeral in parentheses refers to the charge on one of the metal atoms. In our next example, the compound has 3 iron atoms, but the charge written as Roman numerals in parentheses will be the charge on 1 out of the 3 irons. In this example, we're trying to find the name for Fe3PO4-2. First of all, we don't know the charge on the iron because it's a transition metal. So we're going to have to figure it out based on the fact that it's bonding to 2 phosphates. We know the charge on each phosphate is a -3, and there are 2 of them. So there's a total of -6 charge coming from the phosphates. We also know that the total charge has to be 0 in order to make a neutral ionic compound. If we've got -6 on the right side of the chemical formula, then we must have a total of +6 on the left side. But that +6 is not the charge of one of our irons. It is the total charge coming from all 3 of our irons. If we divide that +6 charge into the 3 irons that we have, 6 divided by 3 tells us that each individual iron is contributing a +2 charge. When we write the name of this compound, we're going to write iron, and then something in parentheses, and then phosphate. In this case, we figured out that the charge is a +2. So we're going to write the Roman numeral 2 in our parentheses next to the iron. The name iron 2-phosphate tells us that the compound has iron 2 ions and phosphate ions. Again, this is really important. That Roman numeral is not the number of iron atoms, and it's not even necessarily the number of phosphate atoms. It is just the charge on the metal, in this case, the charge on the iron. What is the correct systematic name for FeO? Is it A, iron oxide, B, iron 2 oxide, C, iron 2 oxide, or D, iron 4 oxide? The correct answer is C, iron 2 oxide. The oxide ion has a -2 charge since oxygen is in group 6A of the periodic table. Since the compound must have 0 overall charge, the iron must have a +2 charge. We include that charge as Roman numerals in parentheses. Just like with all of our other ionic compounds, as we go from the name to the formula, we're going to first figure out the charges and then do the crisscross rule. Let's say we were given the name manganese 2 bromide. That 2 in Roman numerals in parentheses is the charge on the manganese. We don't even need to do anything like figuring it out from the periodic table because we can't. We just take it directly from the name. And then for the bromide, since it's in group 7A, we know it's going to have a -1 charge. Again, we're going to do the crisscross rule. Manganese has a +2 charge, which we know from the name, and bromide has a -1 charge. The 2 from the manganese goes down next to the bromine, and the 1 from the bromine goes down as an understood 1 next to the manganese. We write our formula as MnBr2. Again, we're going to make an electronically neutral compound. We've got 1 manganese with a +2 charge, and that's balanced out with 2 bromines, each with a -1 charge. What is the formula for lead 4 sulfide? Keep in mind that ionic compounds are 3-dimensional arrays. The formula of ionic compounds isn't the exact number of atoms of each type, but it's actually a repeating pattern with a ratio expressed in the formula. When we write the formula for an ionic compound, we want to express it in the lowest whole number ratio. If you get a number that can be simplified for ionic compounds, you will want to do that. In this problem is the answer A, Pb2s, B, PbS, C, LaS4, or D, PbS2. The correct answer is D, PbS2. The lead has a +4 charge, which we know from the Roman numerals in its name. The sulfide has a -2 charge, which we know because sulfur is in group 6A. When we crisscross, the 4 from the lead goes down next to the sulfur, and the 2 from the sulfur goes down next to the lead. We end up with Pb2s4. To get the lowest whole number ratio, we divide each of our subscripts by 2, and we end up with PbS2. Notice that the 4 in Roman numerals is neither the number of lead atoms nor the number of sulfur atoms. It is just the charge on the lead. For this reason, there is no reverse crisscross rule to go from the formula to the name. Here's a summary of some of what we've talked about with ionic compounds. Ionic compounds can contain polyatomic ions, but the ones that don't will contain a metal and a nonmetal. We want to look at the metal and see whether it's only got one type of charge. That is, if we can tell from the periodic table what its charge will be, or whether it has a variable charge. If it has only one type of charge, we're just going to name the metal directly from the periodic table, and then name the nonmetal with the IDE ending. For example, calcium is in group 2A, so anyone with the periodic table can know its charge is going to be a +2. Therefore, we don't need to include a Roman numeral 2 in parentheses. The name of CaI2 is just calcium iodide. On the other hand, if the metal has a variable charge, in addition to the name of the metal from the periodic table and the name of the nonmetal with the IDE ending, We're also going to include the charge of the metal in Roman numerals in parentheses. For example, with FeCl3, we know that iron is a transition metal, so we're going to need to include its charge in Roman numerals in parentheses. There are 3 chlorines, each with a -1 charge, so the iron must have a +3 charge. Therefore, FeCl3 is named iron 3 chloride.